Okay, so for today's video, before we get into the actual experimental demonstrations with this configuration, I just wanted to do a quick overview of this high voltage transformer. So first, I'm just going to kind of show you where in the reference material I looked to find the inspiration for this design and kind of talk about why I chose to build it like I did and how I hooked it up with the rest of the circuit. And then after that, we'll get into the actual experimental demonstrations as outlined in this text. Okay, so here we are again with the inventions, researches, and writings of Nikola Tesla. If we go to, so like I said in the last video, the part where our experimentation is going to begin is here on page 145. This is the beginning of his first lecture given in 1891. And a lot of the initial demonstrations, or the demonstrations throughout this lecture, rely on looking at phenomena occurring on the output terminals of a high voltage transformer. So here, these are some of the units which he was using to produce high frequency input voltage with a high frequency alternator. But as mentioned before, we're going to just stick with the capacitive discharge method for our source of high frequency currents. Here is where he's starting to show some of the output effects on the terminals of these high voltage transformers. So in the text, the secondary with its two terminals on either side is depicted like this. So it's just sort of a cylindrical looking object with two metallic posts coming up. And then there are also metallic extensions coming from those posts, which are, I guess, movable or adjustable depending on what experiment you're trying to do. And what he does first is he varies the input current and frequency of that input current into this transformer and observes how the discharge changes in character. So he notes 5 different types of discharges. And we'll be looking at this a little later, but for now, like I said, we're just going to be going over the transformer design. So yeah, we can see that the transformer designs he's depicting here look pretty similar, and same throughout these pages. So the way we can kind of understand what this is if you go to page, I got it marked here, page 170, he kind of shows what's going on here. So the outer part of the cylinder is a secondary coil with many turns of thin wire. And inside of this outside cylindrical shape, there is this primary coil, which is fewer turns of thicker wire. And that primary coil gets inserted inside of the secondary. So it's a kind of a standard high voltage, high frequency transformer type of design. Now later on, he goes on to show a different type of transformer design, which he thinks shows a lot of potential for this type of research. So you can see it's looking pretty different from the other things we've seen so far. We'll go over kind of the reason why he's saying to do it like this as opposed to like the other way we saw before. But it basically has to do with preventing any unnecessary arcing or discharges which occur internal to the coil. You basically want all of your energy to be showing up on your two output terminals, and you don't want any energy to be stuck up inside of the coil or to be lost inside of the coil. That's something you want to try to minimize as much as possible to get the strongest output effects. This is kind of showing our experimental setup that we have right now, and this is just showing that it's just a transformer, pretty much a high voltage transformer. So this right here corresponds exactly with what we have. You may have noticed that, since my last video, I did notice that I had the capacitor and the spark gap switched. where I had the spark gap. I had the two outputs coming from the neon sign transformer going across the spark gap, and I had the capacitor in series with the transformer. So I've just swapped the two. It'll work either way, but like I said, we're just trying to keep as close to what is described in this book as possible. So I did just go ahead and swap the two. So now that we have the output from the neon sign transformer going across our capacitor bank, and the spark gap is actually now in series with the primary of the transformer. This is actually, so now we're past the first lecture and into the second lecture, and he has sort of perfected that high voltage transformer design that we were looking at a little earlier. You can see that he actually, not only now are the secondary halves split, but he's also split the primary windings into two sections as well. And we'll talk a little bit more about the actual geometry of each of these windings and how they were wound and the purpose for doing it like this. Okay, so first let's just go over some of the basics here that we're gonna need for analyzing the output of this transformer. So I've just drawn just a basic kind of coil design where I have the current coming into the coil, like in this direction. And that's going to develop a voltage across the whole coil. So basically what this is going to be doing is, on this coil, we're going to have a certain amount of turns around the core. And based on the voltage across the entire coil, that voltage is going to have to be distributed across the whole of the coil. So if you have a coil and you're outputting, say, 100,000 volts, you're going to basically have that voltage distributed, not necessarily evenly throughout the whole coil, but it's going to be affected by the geometry of the coil and what you're inputting into it. But in some way, it's going to have to be distributed across the turns of the coil. And what happens is, if your potential gets too high and your voltage gradient turn to turn gets too large, your coil is basically going to start arcing over. So the turns that are on the sort of middle part of your transformer are going to be losing energy. So the energy is not going where you want it to go on the outputs of the coils, but it's going to be lost in the middle of the coil because your voltage gradient is too high and your arcing or your bombardment is too strong due to the high electrostatic effects. So this is pretty much what we want to avoid in our system, because what you'll notice is that even though you're able to generate, maybe you got your circuit all nice and tuned up and you're able to generate really high potentials theoretically at your output, you may see that you're still getting fairly weak discharges on your terminals. And the reason for this is basically if you're arcing inside your coil, the energy is not going to where it should be going on your output, but it's getting lost. So that's something that I see quite a bit on all my systems. Any sort of arcing that occurs on anything that's not the outputs where you want it to be arcing based on what you're studying or you're trying to do, you'll see the output falls drastically on the outputs whenever you have that arcing occurring inside your system. So that's basically what we're trying to avoid here, because the whole idea of this transformer is to get some really, really high voltages out so we can study what we want to study. So let's see how Tesla kind of got around that problem. So this drawing here is kind of showing the secondary geometry that Tesla outlines in his transformer design. So you'll see that now, instead of having a single coil as our high voltage output coil, it's been split up into two different sections. Each section is sort of the mirror of the other. So if you'll notice, in addition to splitting the coil into two parts, the directions of the windings has also changed. So here, looking at it from this side, I have the windings going clockwise, and then as we connect in series to the next adjacent coil, the directions of the windings actually switches. So if you follow it, it goes clockwise here and then connects to the next coil and it switches to counterclockwise. And the reason for doing this, I'm still kind of thinking about, but when you put a current into this coil going this direction, you're still going to get this potential gradient from positive to negative, or from the highest voltage to the lowest voltage, going from this end to the other. But you'll notice that you will get some cancellation effect for the magnetic field that arises when you impulse a current into this coil. Because here we have, the windings going one direction, creating one direction of magnetic field surrounding this coil. And here, when that reverses, we'll get the opposite effect. And there must be some sort of cancellation effect going on, which is assisting this coil and not arcing. So here's the page that goes over in the most detail what we got going on here. So we're looking at his transformer design. We have a wooden box here, and inside that wooden box there are two hard rubber spools where the secondary coils are wound. So it's kind of hard to show it in this picture, but he says that these secondary coils are wound with mirror image symmetry, or he says that they're wound oppositely to each other and connected in series over this primary connection here. In the middle, we have a wooden spool, and on top of that wooden spool, we have our split primary windings. So here, he actually has two completely isolated primary windings coming into this box. So you'll see here on the top, we have 4 different wires coming in. Those are the inputs and outputs for each of these primary sections. So they are actually 2 completely separate sections. And that's because there are multiple different configurations that you can run. Let's look at it. Oh, it's the other direction. So he is kind of experimenting with a couple different configurations with these split primary windings. So in this setup, he's showing that there's some sort of capacitance between them, and that's to help give a higher current injection to try to overcome the inertia of these primary coils. You can also just run these in series, so you can just connect these two together if you want to maybe do some lower frequency stuff and get a lot of inertia on that primary, or you can connect them in parallel. So there's a lot of different options that you can kind of choose from when you're setting it up. But basically here on page 207, he kind of shows a picture of this coil. And then here on 208, he actually gives some numbers and some measurements. So you can actually get a pretty close replication of what he had here. So this is pretty much what I was using to, this is what I pretty much based my whole design off of. So now let's go ahead and look at what we got. Here's a look at the transformer that I built here. Again, just a little side by side. That's not it. Here's what Tesla was showing in his lecture for what he had for his high voltage transformer. And here's what we got going on here. So here's the wooden spool here in the middle of the transformer. And that is my wooden spool that I have. Here on the other page, he kind of shows he actually gives some measurements that kind of indicate the spacing between these 2 sides here for his hard rubber spools. So these were constructed according to what he outlined there. I printed this with a 3D printer out of just PLA plastic. So this black stuff here is 3D printed, and the white inner ring here that these black parts are fastened to, or they're actually glued to, that's also just 3D printed PLA plastic. just because trying to get these parts made out of hard rubber would be very difficult. So that's basically all that the supporting structure is constructed with. Is we just have this wooden spool in the middle, like he says in his lecture, and then PLA plastic from a 3D printer. So then in the middle here we have our primary winding. What this is it is a wooden spool with 4 layers of what was this, 14 gauge stranded copper wire. So it's just this sort of stuff. You can just buy it at Lowe's even. It's just 14 AWG copper wire. And you can see here that I just bring out the connections to these connectors here, which I'll eventually stick up through the top part of the box that this is going to go into. But we do have 2 connections for each primary. So like I said before, we can kind of configure the primary in a couple of different configurations. So leaving all 4 connections free will allow us to do this later on. I'm also trying to keep the high voltage outputs separate from these primary connections coming in. So you can see they're actually on opposite sides of each other. But basically, if I were to bring the high voltage parts out of here, we would be at risk of arcing over to these primary connections. So I tried to isolate those as much as I possibly could. So yeah, I wound he actually gives in his book here the number of turns on the primary and secondary. So that was pretty helpful. For my secondary winding, I have this thick high voltage wire on the output, but that's not actually what I wound the entire coil with. It's actually wound with 24 gauge silicone wire, so you can kind of see some of it sticking out right there. But it's much thinner than this, and that was just so everything will fit and we get the proper spacing between the turns. So one thing I also did when winding it is I basically just wound a layer of turns and then hit that layer or covered that layer with some electrical tape, and then did the next layer and then covered that layer with electrical tape, so that we basically have alternating layers of wire and electrical tape on side. And this is just tried to, you know, increase the dielectric strength as much as possible on the interior of the coil, and just to try to avoid any sort of arcing that may be going on inside of here. And that is pretty much it. So there we go. It just sits here in this box. This is just a wooden box. There was actually no metal used in the construction of this. It was my grandpa actually built it for me, and he used wooden dowels here and wood glue to adhere everything together. And then on the inside, you'll notice it's got a little bit of a glossy kind of finish. That's actually this liquid rubber stuff that I use to coat all the inside with. So that way, if I start doing some stuff that will require me to use some, you know, really big currents going into the primary, so we're generating some really high voltage on this thing, it will probably be necessary to submerge this thing in oil for the higher dielectric strength, so we get less breakdowns. But I really kind of wanted to test out the coil pretty good before I filled this thing up with oil, because once I do, it becomes pretty tough to, you know, move around and work with. So I have not filled it with oil yet, but that's kind of the plan here coming up in the future. So now I'll just put the coil in the box and we'll just see what that looks like. So this is showing the transformer inside of the box, or the wooden enclosure. I've gone ahead and mounted it just on top of some little wooden pieces there at the bottom, get it up off the floor a little bit. The transformer in Tesla's lecture is also sitting on top of a little piece of wood, so I guess that's similar. So now we just have these 6 connections here, 4 from the primary, 2 from the secondary, and we need to bring that out up through the lid here. So I'll go ahead and do that, and we'll hook it up to the system and run it. Okay, so I've connected the transformer back into the system. So what I have here is I just have one primary coming out here, and the other primary is coming out here. And these are the 2 high voltage outputs. I've just attached these little wires here on the end just to give us some kind of electrode for experiments. So what you'll notice here is I have this hooked up in a parallel connection right now. So I have the outer side of this coil connected to the inner side of the other coil, and vice versa. And this is because if you connect it the other way, when you try to put them in parallel, and you get the magnetic fields of each of these primary coils going in the same direction, the currents that it will induce and the secondary will actually fight each other and cancel out, and you'll get pretty weak effects. And that's kind of what I was doing at first. And then when I started thinking about it, you actually have to hook it up like this, and then you get your strong output effects. And this is just because in the primary coils, I think you have to hook it up so that it induces currents in the secondary coils, which will be moving in the same direction and not fight each other. All right, so I got everything all hooked up now. Once again, you know the drill. It's pretty late, so I have adjusted the spark gap down to basically next to nothing. Let me just adjust that a little bit. But yeah, we got a very tiny spark gap and a very small gap on our output. And that's just because, once again, it's pretty late and I don't want to make a whole lot of noise here. So this will be running in not a very loud configuration, but we'll just be able to see that it's kind of working, doing its thing, you know. So we'll come over here, flip it on, and we'll start to turn it up a little bit, and I'm going to be looking at the output here. We'll just put the lights off. So you can see it's we're putting pretty high frequency into this thing, pretty quick impulses one after the other, and we get a nice steady arcing stream from electrode to electrode, and it's actually very quiet too. A lot of the sound you're hearing right now is coming from the spark gap, not the actual discharge. If I put my hand over it, I can feel a good amount of heat coming from it. It feels like I'm putting my hand over a candle right now. But anyway, that's kind of just a little demonstration. So what we're going to do for the next video now is we're going to go through and start working on sending different types of inputs through the primary, and we're going to observe how that changes the character of the discharge. And we're going to try to get the 5 different types of discharges that Tesla describes at the outset of his lecture here. So that's it for this video.